So in this video we will be talking about chemical equilibrium. So with chemical equilibrium, basically the rate of a forward reaction is going to equal the rate of a reverse reaction during a chemical process. And I definitely want to emphasize that we are talking about rates. So keep in mind that whenever we refer to equilibrium or equilibria, we are referring to rates when we are speaking in terms of a chemical definition. So we will be talking a lot about concentrations from this point forward at which chemical equilibrium is going to take place, but that doesn't take away from the fact that the definition of chemical equilibrium is a reference to the rate and not the concentrations involved in that process. So let's move forward and talk about a generic chemical reaction. For example, if I have A plus B and I draw some equilibrium arrows leading into C plus D. Now keep in mind this C plus D, these are going to be our products, and A plus B are going to be our reactants. Now A plus B leads into C plus D, as I've mentioned before, and let me just emphasize these arrows really fast to show that we are referring to a forward reaction, and we are also referring to a reverse reaction going in this direction. And that's what we mean by equilibrium. Like I said before, the rate of the forward reaction is going to equal the rate of a reverse reaction, and it'll be drawn this way. Now, with that being said, sometimes I'll see arrows drawn like this to try to imply equilibrium, and actually that's not correct. That actually implies resonance, and we will not be speaking in terms of resonance when we are talking about equilibrium. Resonance will be mentioned in further detail when we talk about organic chemistry. So for this video and for equilibrium, we will be showing arrows that look like this, and we will not show anything that looks like this because, as I mentioned before, this is to indicate resonance and not equilibrium. So now let's talk about equilibrium constants. And an equilibrium constant is just basically going to be a capital K, or it'll be represented by a capital K. And when I say capital K, I'm saying that specifically because I'm not referring to a lowercase k. A lowercase k is going to refer to a rate constant, while a capital K is going to refer to an equilibrium constant. And so I want to make that distinction very clear. Now, with that being said, we are going to have a lot of different Ks, and all of them are going to say the same thing. All of them are going to be expressing equilibrium, but they will all have different subscripts to help identify what type of equilibrium we are talking about. So for example, you might see KEQ in a subscript, and that's just a very broad way of saying equilibrium. Now, you might also see something that says or shows KA, KB, and these are going to be, this is an acid dissociation constant. At equilibrium, Kb is going to be the conjugate base of an acid, and that's going to be a constant as well at equilibrium. Now we will also have Kc, Kp, and Kc is going to be a concentration at equilibrium. Kp is going to imply pressure at equilibrium. So I mean, you can see how there are a lot of K's, and by the way, I've only drawn I haven't drawn all of them. There are a lot more than this, but I just wanted to make the point that you will see a lot of K's, and they all mean the same thing. So when you see them, don't think that they're all confusing, and there's just too many to try to remember. I mean, they're all saying the same thing. They're all saying that they're all basically implying that you're talking about equilibrium, and the subscripts that are attached to them are going to tell you what you are talking about and what you're referencing as far as what is at equilibrium. So I wanted to make that point clear. Now that we've talked about K's, I think we can talk about equilibrium expressions. And let me just change my colors up a little bit. So an equilibrium expression is a K where I have my products over my reactants. And that's what the equilibrium constant represents. It represents products over reactants. And you'll see them drawn with brackets around them. And these brackets are going to imply concentrations, or more specifically, they are going to imply molarity. And just a quick refresher, molarity is going to equal moles of solute over liters of solution. So that's just a quick refresher on that, but that's what will be implied in these K values, and sometimes you'll see something else that could maybe indicate atmospheric pressures or something like that, but for the most part you're going to see everything drawn out in molarity or in terms of molarity. So let's continue on with these equilibrium expressions by demonstrating a generic formula. So if I have a formula, or a chemical formula, for example, where I have show my equilibrium arrows, I can translate this information by showing a K value. And I can demonstrate that by showing, once again, my products over my reactants. And that's simply going to be drawn like this, where I have my C, so those are my products over my reactants. Now notice how I took my lowercase letters and turned them into exponents when I drew out the expression. Now that's going to be typical, and these lowercase letters are going to be simply referred to as stoichiometric coefficients. And when I say that, what I'm referring to is you're going to see a balanced chemical equation when you draw out these equilibrium expressions, and you never want to include an unbalanced equation into an equilibrium expression. You're always going to want to balance the equation in order to determine the correct expression when you're translating this information over. And so I want to make that point clear. Now the next thing is, notice how I didn't show any states of matter. For example, gas, liquid, solid, so on and so forth. I left those blank. And those are going to be extremely important moving forward, and we will be talking about those here shortly. So let's just show another example where I demonstrate some of those states of matter that I mentioned earlier as far as solids, liquids, and gases, and let's just show that with a real chemical equation. So for example, if I have, let's just say, hydrochloric acid, and I suppose I can add oxygen, my equilibrium arrows, and then I throw some water in here, and I add that to chlorine. Now let's add our states of matter, our phases that we are in, and we can do so by, we'll call this a gas, a gas, and we'll make this a pure liquid, and we'll call chlorine a gas as well. So now let's translate this information and put it into an equilibrium expression. So if I have a K, I can then translate it by, once again, these are my products, next to my reactants. So if I translate this information over, based on what we've learned so far, we will have H2O, and we will have chlorine with the stoichiometric coefficient on top, and then we will have hydrochloric acid with its stoichiometric coefficient, and oxygen. So that looks correct based on what we've learned so far, but one thing I need to mention now is that there are certain phases of matter that can be neglected and omitted. So what I mean by that is if you see a pure liquid, it could look like this, or if we have a solid with just an S, or if we have a noble gas, all of these can be omitted from our equilibrium expression. And in this case, you can see that with water, we have a pure liquid. So actually, we do not have to include this into our equilibrium expression. And the same is true for solids and noble gases as well. Now we only have regular gases right here, so we are okay with that. But for future reference, if you see any of these, then just know that you don't have to include those into your equilibrium expression, and therefore, when you're running calculations based on that, you're not going to have to reference those calculations. So let's just finish this out. So now K is going to equal chlorine with our stoichiometric coefficient on top as an exponent, and then we're still going to have our hydrochloric acid next to oxygen. So that will be our final answer as far as equilibrium expressions are concerned. Now one last thing I want to talk about is, since we are talking about Ks, I want to talk about some of the values that Ks can represent and what they may imply. So for example, if I have a K value that is greater than 1, well, that's going to imply that my products are favored. Let me just rewrite this. And that makes sense, because if we were to draw out our equilibrium expression, we would see K where we have products over reactants. And in order to have a value where K is greater than 1, well, we're going to have a higher concentration of this than we have in our denominator. So in other words, the numerator will have to have a higher value than what's in the denominator, and that makes sense mathematically, because if it were any other way, then you wouldn't have a K value that's greater than 1. Now, we can prove this graphically by demonstrating it like this, where we maybe show something where we have concentrations on our y-axis, and then we have time on our x-axis. So if we show some curves, such as like this, and by the way, these will be our products. This will represent our reactants. We can see that if we trace it back, at equilibrium, we have more products than we have reactants. And notice how the products and reactants, once they reach equilibrium, we'll say that it's probably at this point or somewhere in there, they do not change with time. So that's just an indicator that the rate of the forward reaction is equaling the rate of the reverse reaction, and therefore your products and reactants are not changing with time from that point forward. So that's when k is greater than 1. Now let's change it up a little bit and show what happens when we have a k value that is less than 1. So if I have a k and now we're less than 1, now our reactants are going to be favored. And if our reactants are favored, when we draw our equilibrium expression, once again it's products over reactants. Well, in order to have a value that's less than 1, we are going to need a higher concentration in our reactants than we have in our products. And once again, that makes sense because if it were any other way, we would have a different k value. So that is how we are able to attain a k value less than 1. Now, if we were to, once again, demonstrate this graphically, we would show it with something like this, where our x and y axis are going to be the same, by the way, where we have concentration. And I'm just going to put brackets around here, but this C demonstrates concentration. So I'll draw some curves. Now over here we are going to have our reactants, and down here we will have our products. If we trace it back, we can see that we have a higher level of reactants than we have products once we reach equilibrium. And in equilibrium looks like it'll be reached at about this point right here. And once again, these reactants and products do not change with time as they move forward in this direction. So now the last thing I want to talk about is when we have a k value that is equal to 1. So if I have a k and it's going to be equal to 1, well, that's going to suggest that neither my products or reactants are going to be favored. And if we demonstrate that mathematically, we can say that K, once again, is products over reactants. Well, the only way to gain a value of 1 would be to have the same amount. So if we have, I mean, in other words, whatever we have for our products will have to be divided by the same amount in our reactants. And that's the only way we're going to be able to get a value of 1 in terms of ratios. So that's how we are able to gain a value of 1. Now, if we were to demonstrate this graphically, once again, we can show that by doing the exact same thing. This is concentration on my y-axis, time. So now, when I'm drawing my lines, you can see that if we trace this back, products and reactants are going to be exactly the same. And this right here, by the way, is supposed to represent my products and reactants. And so that's how we were able to get a value of 1. So I hope that was helpful, and we will be continuing with an additional equilibrium video following this one.